on continuity, that f of x is continuous at x equal to 0. But that example we just looked at a little while ago, we showed that the function mod x is not differentiable at x equal to 0. So here's some examples of when a function is not differentiable. And we discussed a little bit earlier about, in order for a function to be differentiable, we want it to, in some sense, to be smooth. We want the function to be, so the slope, in other words, is there mustn't be any jerks or jumps or anything extreme changes in the slope of the function. So in number 1, when the graph changes direction suddenly, so there's a corner, and that would mean that the left limit is not equal to the right limit in the derivative. So we've seen if that's the case, then it's not differentiable. If it's not continuous, then it can't be differentiable. So this would be at any point where there's a discontinuity. So if there's a break in the graph in any way, it could be a jump discontinuity, it could be a step discontinuity, could be a removable discontinuity, could be an infinite discontinuity. And here we go. If f has a vertical tangent at x equal to a, so that's where the limit tends to infinity. So there's a couple of sketches there to show there. Obviously, we know there that the slope is undefined, and so the derivative does not exist where there's a vertical tangent. Okay, so looking at higher derivatives now. If f is differentiable, then f prime of x is a function of x, so as we've seen. So then f prime may also have a derivative, f prime prime, or we say f double prime. So we call this f double prime, and it is the second derivative of f. So it is the derivative of the derivative. We can also use Leibniz notation to write like this. So this is prime notation here, and this is over here, Leibniz notation. And we read this as d2y by dx squared. We can also say d by dx of dy by dx. So that means the derivative of dy by dx with respect to x. Or we can say f double prime, f double prime of x. These all mean the same thing. And when we differentiate the derivative, which is a function of x, we get a function of x, if x is the variable that we're talking about. So the second derivative is a function of x, which means we can find the derivative of that. And we can keep going. So this is f triple prime of x, which is the derivative of the second derivative. We'd say d by dx of d2y by dx squared, or d3y by dx cubed. We can generalize this to the nth derivative, whether you're using prime notation or Leibniz notation. You'll see there that the derivatives there, the nth derivative of f. So just as an aside here, it's important to distinguish between the derivative. So if we want to write the nth derivative of f, we write it, and we put the little superscript here, the n, in brackets. So for example, if we wanted to write the fourth derivative, and we use, after 3, we use Roman numerals. So for the fourth derivative with respect to x. So distinguish between the nth derivative and so we put the n in brackets, and for e.g. a power of f. So if, for example, we want f of x cubed, we would write f3 here, no brackets around the 3, is f of x all cubed, okay, and also the inverse. So let's say and the inverse. So the inverse function of f, which we denote f minus 1 x, f inverse of x. And the reciprocal would be 1 over f of x. Would be f of x to the minus 1 is the reciprocal. So we've got to distinguish here notationally so that we know what we're talking about. All right, so important that if you're finding derivatives, we put the number of the derivative in brackets and distinguish between the inverse function and the reciprocal. We did talk about that when we did inverse functions. Okay, let's look at the example on page 22. If f of x is x cubed minus x, find f double prime of x, f triple prime of x, the fourth derivative of x, and the 100th derivative of x. Right, so f of x is equal to x cubed minus x. We have found out already in a previous example that f prime of x we found to be 3x squared minus 1. Now we want the second derivative. F double prime of x is d by dx of f prime of x. And by definition, that is the limit as h tends towards 0, f of x plus h, this should be f prime of x plus h minus f prime of x all over h. So this is the limit as h tends towards 0. Now we put x plus h in place of x in the first derivative. So limit as h tends to 0. This is 3 into x plus h all squared minus 1. So that is f of prime of x plus h minus f prime of x, which is 3x squared minus 1 all over h. Multiplying out and cancelling, we get the limit as h tends towards 0. We get 3 in the numerator, 3x squared plus 6xh. That's h squared minus 1 minus 3x squared plus 1 all over h. When we do some cancellation here, the minus 1 cancels with the 1. So we get then the limit as h tends towards 0. Take out an h common factor in the numerator, leaving us with 6x plus h all over h. So h is tending towards 0, not equal to 0, which means we can cancel the h's there. And we get the limit as h tends towards 0 of 6x plus h. So that's just equal to 6x. Now we want the third derivative, f triple prime of x. So that is d by dx of f double prime of x. So we're taking the derivative of the second derivative. Now, according to the definition, limit as h tends towards 0, f double prime of x plus h minus f double prime of x all over h. And the f double prime is the 6x. So that is equal to the limit as h tends towards 0. We've got 6 into x plus h minus 6x all over h.